Nice.
We're gonna do a review.
Nice.
Nice. Gotten somewhere.
Was there chapter 1 homework? So you got chapter 1. Was there chapter 2?
I didn't see a chapter 1 up there when I walked in.
No, I just printed. They were there on Tuesday.
Oh, yeah, no.
Okay. But yeah, you need a chapter 2. I think they got eaten somehow. I'll print you one after, or like after our break period when we're kind of quizzing.
Perfect.
Don't know how that's possible. Print more. I always print more than there should be, and they still all get taken.
I wonder how that happens.
to do club announcement first?
Yes. So I want to give a quick announcement before we get started with class. My name is Max Keidel. I am the president of the RCC Music Club. I just wanted to let you guys know a little bit about what we do as a club and some of the events that we're going to have this term. Our mission is creating a community through music. So in doing that, we have jam sessions during our meetings. We try to get together as a community to make music, to teach music, to talk about music. And one of our big events that we're planning for this term is going to be a holiday caroling event. If any of these things interest you, or you just want to figure out how to get involved, you can easily contact me. My information is on one of these flyers. If you want to get signed up with our club's mailing list, you can easily scan this little QR code right down here, and it will direct you to a Google form. I'm going to pop these over here, and after class, if you want to take one, you absolutely can.
Did you want to put your email on the board or anything?
Yeah, I can do that.
Just put it over there. Anybody else want to make any club announcements or ASG related announcements, business? I'll let you finish writing that up, Max. And we'll go over. So definitely encourage y'all to find a club this quarter. You know, if not music club, then, you know, another club or start a club. Eventually I'll make a Earth Club announcement thing, but I was not prepared today. All right, so some things we should talk about. So let's talk about due dates, because I forgot to mention that. And so due dates, I'm fairly flexible with due dates. So kind of the general consensus is that homework is due the next Tuesday. And again, it's a little heavy this week since we have kind of 2 chapters to fit, right? We're just trying to get on board with all the background information we need to kind of get to Gen Chem. So yes, you do have 2 chapters this week, but you know, I think you should be able to do it. If you need a little bit more time, that's okay. Just let me know. You know, get help. I'd rather you turn in your homework a little late, but then you ask help for it, right, and then get it in correctly. And again, I don't check your homework for accuracy. The answers are posted, so it's meant to help you study. And your homework, right, is meant to help teach you what you don't know so that you can study it, get help with me, look at your book. You know, you can look at YouTube videos. There's tons and tons of resources. And then generally labs are due a week after. So if you are on the Tuesday lab, I would like it, you know, next Tuesday when you're in lab. Same thing Thursday, you can turn it to me in lab. And again, if you run into difficulties, not a problem. I'd rather get it late and then you get help from me. So those are due dates.
Do you want it on Blackboard or paper?
I prefer a paper copy. Yeah. Blackboard is, like I said, kind of a mess, but question.
Those reading questions you were saying were on Blackboard also, those expire at the class time the next week, or do
They shouldn't. So even though they're due, they should still be open. If they do close, let me know. So yes, that's a good reminder. So again, those reading questions are on Blackboard, so you do need to go to Blackboard for that. And if you need help accessing Blackboard, you know, let me know. We have a computer lab, so if you don't have a computer, right, use the resources. So again, just get help. Make sure you do those reading questions. And again, it's supposed to help guide you with the book. The other thing I wanted to mention, so if you were in lab, you saw that we have a journal article connection. And so RCC has bought the Journal of Chemical Education such that you can access these journals. And so you either have to be on campus, or if you're off campus, I think it'll just prompt you to log in, and then you just use like your student login credentials. And then if your student credentials don't work off campus, let me know, because then it's just an error. But I was going to show you how to find that. So, okay, we're on the RCC webpage, and you could probably search library here. Otherwise, you can go to your student center and then go down on the side here. So you have library services. And so again, this is just for like the little RCC library. And then scroll down. So then go down to guides here. And then chemistry. Click on chemistry. And then up at the top is the Journal of Chemical Education. That's odd. We're on campus. So testing that out. So it should just take my credentials. It did. I don't know why it thinks I'm using a VPN. That's why. Sorry, I answered my own question. And it should come up with access provided by RCC. And now you have the whole Journal of Chemical Education. And you guys can, of course, knock yourselves out, right? Again, these are kind of easier to read, but you might find something interesting in there about how to teach chemistry, how to learn chemistry. So different resources there. Okay, is that clear on how to get to the journals? And then other things I kind of forgot to mention. I brought it with me. So again, feel free to look at these chemistry and engineering magazines. I specifically brought this one in because I know it's falling apart. They destroyed my magazine. It's this month's issue, but this one it featured an article about chemists with disabilities. So I wanted to leave it there for you guys to read. But chemistry is considered pretty ableist as a subject. It has a bad reputation, right, of being ableist. I've known those disabled chemists, and obviously there's difficulties with working in a lab, but accommodations can be made, and you can kind of read there on how they had different assistants that might have helped them, depending on their disability. So I mean, just always good inspiration, right? No matter what challenges you may face, hey, you can still go on to do whatever you're interested in. Any other thoughts, comments, questions? All right, let's continue rolling. And the end of Chapter 1 just wants to kind of go over the units. And I think this is a good place to also, again, look at our dimensional analysis and remind ourselves kind of where units come from. And so we have our standard unit of energy, which is joules here. And does anybody know what joules, like what the other units go into a joule?
kcals.
Not kcals. So kcals would just be another form of energy unit.
Joules are derived.
Isn't it watt per second or Newton meter?
So Newton meter would be good, but what about other units? And yeah.
Kilogram.
You got part of it, and you could look at this if you needed a hint.
Okay, kilograms times mass squared per second squared.
Not mass, but
Kilogram meter per second squared.
yeah, meter squared over second squared. Excellent. And so obviously we had a little bit of recall issues, but that's perfectly fine, right? So I have that there on purpose so that we could see, oh yeah, let's compare that to our kinetic energy formula. Now we can rederive those units, which you guys were excellent at recalling. And so in physics, right, mass is typically given in kilograms, so that's kind of the only little tricky caveat is this is in physics land for a second, so that's why it has kilograms. And then again, you all puzzled it out correctly, so of course this is V for velocity, so meters per second, and then obviously squaring it to get us our joule unit. So again, right, good techniques. If you're lost in physics, well, you can always rederive, again, your formula from your unit. So joules is equal to that. So, right, if you're ever staring at joules, we'll go back to this. And of course, right, you have the Newton meter as well, but you may not know what a Newton meter is. So, and then we kind of briefly mentioned it yesterday, right, where I was talking about kind of our laws. And so we can, again, make connections, right? So these would be our laws then, if we're thinking about our definitions of theories and laws. And so I had brought up, right, we can, of course, calculate how long that it takes to drop any object over and over again. And, of course, you can relate the two. And so, of course, we have our gravitational potential energy formula, again, just to highlight that we're converting potential energy and then into kinetic energy. And this just gives us a context, kind of just fun facts. So energy that hits the Earth in one day from the sun is, of course, 1.5 times 10 to the 23rd joules. And right, usually if you're seeing an argument over why we need solar panels, someone's going to present to you this fact, right? And then make the argument, oh, if we covered the whole Earth in solar panels, right, we'd have so much energy, which is true. But again, we won't go down the rabbit hole into energy conversion today, just kind of bringing that up. And then world consumption of energy. So this was in 2005. Again, I mentioned this textbook is outdated, but we could, look up kind of current energy demands. And then obviously keeping in mind, the buzzwords of AI or whatever. But all that's really doing is sucking up energy. That's all I see that. And all those right, just think about the infrastructure of the internet, right? It has to run on something. It has to run on servers. Like most of the internet runs on the Amazon web servers, actually. So Amazon invested a lot of money into that. But again, energy. So that's always a constant question of, right, how do we get more energy? What's the most efficient fuel? So then we have, right, energy of the atomic bomb. So 8.4 times 10 to the 13 joules. Obviously, right, that's a nuclear reaction that's out of control, unlike a controlled nuclear reaction, like a nuclear power plant. TNT, so again, nice explosives. And then other just kind of fun things. So average energy, 7 times 10 to the 6 joules. So if you're really bored, you could try to calculate calories back out. And then this is a calorie, so nutritional, and notice that is 4,184 joules, so kind of large. And we'll get into these other measurements kind of later. So energy in a typical chemical bond, 2 times 10 to the negative 19, and we'll kind of see some of this. And energy of the photon, so this will be coming up pretty shortly. And so again, this graph is just kind of showing our relationship between our potential energy and then, right, kinetic energy. So obviously at this point, it has all potential energy, no kinetic. And then of course, if I were to let it go, it would be the opposite. And this is also more for a trajectory. So I'm not going to throw my pen, but right, if I were to make a nice arc, then the arc at the highest point would be the greatest gravitational potential energy. And that all that is to say that, right, our total energy is equal to our kinetic energy plus our potential. But we'll come back to energy a little later. So those are just kind of our broad concepts there.
I forget, wouldn't that term be, I might be thinking of something else, mechanical energy, when you add your kinetic and your potential energy?
Yeah, I mean, kinetic's just kind of more broad, like mechanic would be a subset of kinetic energy. All right. And then other just kind of terms. And so this can come up both in lab, but then these are, again, just like other concepts you'd want to keep in mind if you were designing an experiment, trying to figure out, you know, if your experiment is a good experiment. And so we have our measurements. And again, right, you got a little taste of that in lab, or you will today. And so, of course, you can assess the precision and accuracy of your measurements to determine kind of the quality of your data. And there's a lot of different ways to do this. Again, this is like a pretty broad statement. Won't go down the rabbit hole. And so precision would be if we had like a measured value, right? Or sorry, precision refers to how close they are to one another, right? So basically, is your method consistent? And so, right, this could also show like a systemic error, right? So looking at A here, so the data is precise in the sense that they're all close together, right? But they're off target. And so maybe a good analogy is, you know, you're trying to measure the speed of light or something. You have your setup, but maybe you are off on one of your length measurements or something. So something is slightly off and everything is consistent, but consistently wrong, right? And so again, if you had something like that, you know, maybe you want to analyze your setup a little bit, make sure there's not some sort of systemic error that would be causing that. And then accuracy, again, you don't always have kind of a standard to compare to, but if you did, again, we'll think about our popcorn lab. So kind of the accepted H2O for our perfect kernel was 13.5%, and then, right, you compared your value on Tuesday, or you will today, and see again how accurate you are compared to that accepted value. And of course, again, right, speed of light, that's a good indicator to see how accurate your experiment is. So obviously if you're off from an accepted value, well, you got to figure out kind of what's wrong there. And so kind of looking at these, right, B is at least somewhat accurate, right, not that precise though. And I mean, that could be, it's hard to tell, right? Again, we're just kind of talking in theory very abstractly, but I mean, this wouldn't necessarily raise a red flag. You know, again, it depends what you're doing, or you might want to reevaluate your technique. C, obviously, would be everything is perfect. Yay, happiness. Again, usually things aren't that straightforward. And then D, so D is just kind of emphasizing that you have points all over the place, right? You have one that's kind of almost accurate, but then you have this outlier. So again, you would just probably want to make sure your technique is good, you have a consistent kind of methodology, and that you're able to kind of replicate those results. But again, this gets very field specific and very research specific over what that would be and what makes a good paper, what makes an acceptable paper. Again, that's varying by field. And then this was provided on your lab, and this is a pretty standard calculation that you, I'm sure, have done before, but often you calculate your percent error, and so you take, right, your average value that you found in lab, so from lab, and then subtract the true value, or take the difference from these, and then divide it by our true value times 100. And I feel like people get hung up on like positives and negatives. It doesn't matter too much. Sometimes you even see formulas with brackets, right, indicating the absolute value. I'm not too picky, so obviously if it's negative, right, that's just indicating you're probably under. If it's over, you're over. Or again, absolute value, right, we're just saying we're off by a certain percentage. So again, I'm not picky with that, just find our error. All right, let's look at these sig fig operations, because this is important. And so I apologize if you're the Tuesday people. I try to help y'all in lab, but of course you might want to go over your calculations. And so let's look at these. And so we're just going to look at multiplication and division and addition and subtraction. And so again, right, we want to make sure that we're carrying over the correct accuracy. And so our mathematical operations also dictate how many sig figs we can report. And so I like to start with multiplication and division because I feel like it's kind of the easiest. And by that I mean we just have to determine what the least precise measured value is, and that determines how many sig figs we report. And so let's look at multiplication. And sorry, let's see. I need my calculator. That's one thing I forgot to do is pull up my calculator. If you need a virtual calculator, let me know and I can always send you a link to this. All right, so here's my calculator. And so I'm just going to follow along with our operations here. So looking at what we were given, so we have 3.56. So how many sig figs is this? So 3 times 4. So how many sig figs is this? 1. And so when I'm looking at this, this is kind of raising red flags in my mind. And so hopefully, again, right, if you had lab, you don't have time to correct it now. But for the future, right, you always want to make sure you're giving yourself enough digits, right? And we'll look at that with our ruler. And so I would say probably shorted ourselves a digit here, but we have to go with what we're given. And so let's plug it into our calculator. So we would punch this in. And then, right, calculator spits out 14.24. But then, right, now we have to round this appropriately. So unfortunately, we have to round to 1 sig fig. And then by rounding, so now our 14, right, we have to get 1 sig fig. And so that takes it to 10 there. And follow your units. So, right, centimeters times centimeters, so we get centimeters squared. So personally, right, again, I don't like that, but that's just, we have to go with what has been reported from our calculations. Now let's try our next example. So how many sig figs are in 2.050? Yeah, so we have 4, right? So they bothered to report this, so we know we are accurate to that, so 4 sig figs. And then how many in 5.0? So 2, I see fingers. All right, so again, we'll do our math operation. So 2.0 and then times 5. So we get 10.25. And again, right, we need to now round to 2 sig figs. And so it mentions that this is one of those weird scenarios, right, where we have this kind of 10. Oh. And so, right, we could write it as 10 period, or like it mentions here, rewrite it in scientific notation so we can clearly see that we have 2 sig figs. And again, right, I feel uncomfortable about it just having 1 sig fig. So, right, 3 sig figs, 1 sig fig. So same thing. So I'll be explicit. So 45 divided by 9. So 5. And again, right, 1 sig fig. So we just report to 5 centimeters there.
Don't the centimeters go away for that one? You have
Oh,
centimeters over centimeters?
it would. That's probably not right, but good catch on that one. All right, so now let's look at this last example. And so we have 4.5 and then times 12 inches over 1 foot times 2.54 centimeters over 1 inch times 1 meter over 100 centimeters equals that. But what do we say about our conversion factors? Do they count towards our sig figs? So no. So right, so we just look at our number that we were reporting, right? So we started with this. So 2 sig figs, ignore all your conversion factors, right? So you don't have to take that into account. And so might as well punch it in. So we're all on the same page. So 4.5 times 12, just multiplying across, so times 2.54. And divided by 100. So yes, we get the same thing. And then of course, rounding appropriately to 2 sig figs, we get 1.4 meters again. Questions on multiplication, division? So I feel like that's pretty straightforward. And then if we look at the rule real quick for addition and subtraction, it's fairly straightforward, except I always kind of say you might want to write it elementary school style to help, and we'll see what I mean. And so it says the value with the smallest decimal measurement determines the sig figs. So let's practice that. And so we have our example here. And so it's asking us to just look after the decimal place, right? So when we're adding here, well, this one is reported to 3 after, but this is only 2 after. So we can only go to 2 after the decimal place. And so again, I'll be really explicit here. So typing it in to our calculator like we might do. So yes, indeed, we get 336.677. And then again, we need to round now to 2 after, since that's what we're limited by. And then we get 336.68 inches. And right, so now you have 5 sig figs going forward as well. And so I think this was a common thing that you were doing. You know, obviously you're going to subtract in your lab, in the popcorn lab, so then you might go from like 5 sig figs to like 3 or 4. So again, that's typical, and then you just proceed right with the next operation. So this is another good example. Again, it feels a little awkward to me since they didn't give any numbers after the decimal. So 457 centimeters, and then we could plug that into the calculator just to verify that our example is indeed correct. Okay, so we get 456.32, and then again we have to round to our least precise, so unfortunately we have to round to 456 centimeters. And so I generally like to write it like this, again, to help me. And then you just want to go kind of step by step. So like I was saying, you know, you'll probably do your subtraction step first to figure out your mass of your kernels and your flakes. And then you'll have 3 sig figs, right? And then you'll proceed with the multiplication division operations, again, with those 3 sig figs or however many were remaining. And if you need help with this, you know, of course, ask questions. All right, last thoughts on this before we at least start chapter 2. So we'll see how far we get. All right, so I need to post the notes. They're not live, but I'll get that going. And so chapter 2 now, we're starting to get into the fun part, right? Atoms, molecules, just kind of laying our foundation. And so of course we said that chemistry is a study of matter, and well, matter is composed of particles. So now we have to define kind of all these particles. So we have, let's see, blah, blah, blah. So let's skip down. So, right, we have atoms, or I'll also put here elements, right? So these are our basic submicroscopic particles that constitute the fundamental building blocks of matter. And right, so of course you can tell whether something is an atom or an element by looking at the periodic table. So that's helpful. And right, we have one in the back of the room, so you can always look at that. You have the nice cardstock ones I provided. And then I like ptable.com, so it's a nice online periodic table, and it does give a few helpful resources that we'll get into. And so, right, if you ever have a question about something, is it on the periodic table? So people often confuse like gold and brass, and so gold, right, we know gold is an element, it's on there, right, we can find it. But then if you were to try to find brass, so of course brass is not on there, right, you can look, search all day, okay, not on there. So brass actually is what's called a mixture. So that's going to be zinc and copper. But that's going to take time, right? So it's going to take a little bit of learning and spending time with periodic table and to develop a little bit of chemical literacy. So, okay, so I'm just going to put a little cheat sheet. So found on periodic table, yay. And then, so we'll get into this. So the text for it, right, was up here, but I'm going to rewrite it down here. Oh, I probably can't fit it in. And so, right, these atoms, which we'll get into, have protons, neutrons, and electrons, which are the subatomic particles that we'll look into and that comprise an atom. And so then we also have, of course, molecules, which it defines nicely here as two or more atoms. And we should say two or more different atoms. And so carbon monoxide is a nice simple example of a molecule, CO. And again, we'll get into kind of covalent bonding as well, and ionic bonding. And so, of course, these atoms and molecules determine how matter behaves. So, again, very charged statement, very open statement. But again, that's what we're going to be working towards in this class, is kind of, let's look at the periodic table. Let's look at the periodic table to understand its general properties. That's going to give us an idea how they behave. And we're going to be able to start to explore and understand that reactivity. And so again, just reiterating that our element then is our substance that cannot be broken down into a simpler substance, or at least, again, an atom. So we're saying, right, a molecule is made up of different atoms. And so, right, we have single types of atoms like helium. And again, right, refer to the periodic table if you need to find out whether something is an element or not. And so again, we mentioned our compound is two or more elements, and then kind of the key point is in fixed definite proportions. And so, right, a compound will always react in a certain way, so that's different. Again, I'll kind of put compare to a mixture. And so a mixture, right, is not defined proportions, and maybe some people are better versed in this than I am, but I think people have referred to like sword making, that like we've kind of lost the art of sword making, that they made better swords, you know, back in medieval time because of some certain ratio, right? And there's not a formula, right? So it's not like a combustion reaction where it's going to react, it's always going to make water and carbon dioxide. It's some mixture. And so I've heard people say that we've kind of, again, lost the art of how to make that perfect mixture. And so maybe our steel is not as strong. And again, so steel would be a mixture, and that can have different components to give it different properties and strength. I mentioned, again, brass, so that can be in different ratios. But then, of course, we can take this, I'll move away from metals to kind of make a better analogy, but like Gatorade or tea, right? So people can put varying amounts of sugar and colorant and whatever other additives, flavoring. And so again, right, that's going to be a mixture in different proportions where, again, a compound is something that's defined with a formula. And we'll look at this again more as well throughout the course. And so then, kind of looking at our periodic table, we have our elements here, and so other fun things. So they're always trying to discover new elements, and then we can also think about the form that many of these are found in. And so it kind of makes a statement here that many of these elements are reactive and combine with other elements to form compounds. I mean, I would also put like many metal oxides are how these elements are formed. So, you know, lithium, sodium, potassium, all these are super reactive. So in the next few weeks, we'll look at that alkali metal reactivity. But obviously, they're not going to be found in their pure form, right, when you go to mine them. So they're going to be mainly lithium oxides or sodium oxides, potassium oxides, and then they have to be, right, chemically processed, or, you know, you could also do that electrochemically to actually get out the pure metal. And so same thing with many of your other elements. So we have, right, many of our metals here. And so also starting to take a little tour of our periodic table. So most of the elements, right, are considered metal in character. And so there's different tables, obviously, that all kind of have different labeling. You might find minor discrepancies as well. I like this one because it has our nice color coding. And so we can see that we have our stair step. So this is our semi-metals here. So that kind of separates our metals on this side from our non-metals. So our non-metals are a lot smaller. All right, so, oh.
Well, I guess I have two. The columns, the number that's on top of it is the electrons in the outer shell, right?
Yes, but let's, yeah, I didn't want to go there quite yet.
Well, the question I wanted to ask, I want to make sure I remember it right. So is it 57 through 71, where it's like kind of chunked out? Does that mean that all of those have 3 in their outer electron shells? Or are they supposed to fit in that column?
So they don't fit in this column, and yeah, kind of jumping around. So we'll investigate the periodic table. Let me see if it's, let's see if we can find how it's supposed to be. Because it's really supposed to fit in there, but let's see. So this is a better representation. Oh, come on. Well, that's microscopic.
I think I've seen it where they make it really long and they put it in there.
Yeah, so right, so it would just be inserted there. But we'll get into it, like, hang on, next week we'll get into the shells and how they fill, and we'll get into more details of that. But yeah, you kind of have to envision if we could just shift the D block over and then put those 2 rows there, that would be kind of a better representation. And I could try to find a better, see, this is a better picture.
So the answer would be that no, all those that are like taken out, they don't have 3 in their outer.
Yeah,
Okay.
yeah, so they would fit like this roughly. But again, we'll get into that
Okay.
next week. All right, so let's kind of look at some things. And so let's look at the periodic table. So some, at least, ground rules for a second. So we'll get into a thing. And so I'll start with our number of protons determines our identity. And so we just want to look at our atoms first. But then I want to bring out a few exceptions. So let's just make sure we're all on the same page with our ground rules here. And so, right, just look at your periodic table. So it has this nice number in our upper corner here. And so that is our atomic number. And so your periodic table should have a little reference, right, on how to read the specific one. But, okay, they're in order. So 1 for hydrogen, 2 for helium, 3 for lithium. And so that's just going with the number of protons, right? So you change the proton, you change the identity of the atom. But now let's look at a few special cases. And so we have these things called diatomic molecules. And diatomics just mean that they are an element that is found paired in what I would call its elemental form. So elemental form just means how this element, or right, if we're atom referring to the specific identity, but right, looking at an element, so how this element is by itself. So right, if you just isolate that element. And so that being said, we have 7 diatomics. So hydrogen, oxygen, fluorine, nitrogen, chlorine, iodine, and bromine. And so again, all that means is once you isolate them as a single element, right, they are bonded to itself, but it's still considered an element, so that's what I want to make clear, right? So we don't have 2 different ones, so it's not a compound. And then we can also highlight these, and I'll go back down. But I would, make a note of this on your periodic table. But we have, so hydrogen is kind of the one little exception over here. So we have hydrogen. And then the rest, I like to say make a 7 so you can remember that there are 7 diatomics. So again, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So notice, right, your halogens are diatomics. And we'll get into that. Sorry, I keep throwing out terms. Again, that's kind of the nature of the beginning of chemistry, is like I'm throwing out new words, new languages, but just ask questions, slow me down. We're just trying to get everybody on the same kind of basic page. All right, so we have our diatomics. So again, write those, mark those. So right, they're always found paired. And so we're going to do a demo later today. But I want you all to think about that. So we're going to do our demo today. And why I picked it is because we have simple elements in there. So we're going to do some exploding balloons. So we're going to have a hydrogen balloon, an oxygen balloon, and then a hydrogen plus an oxygen balloon, and then we're going to combust them. And so again, all we're saying is if we're writing out chemical reactions or predicting what we're going to do, they always need to be written like so, right? Because again, they're a diatomic. So when we say hydrogen gas, it is H2, right? Oxygen gas, O2. Does that make sense? All right. And then we have kind of a special class of this called allotropes. So does anybody know the definition of an allotrope, or maybe some examples of common allotropes? Yeah.
Like white phosphorus and red phosphorus?
Yeah. So white, red phosphorus. And then do we have a guess of a definition?
Different forms of an element, like different elemental forms.
Different forms. I'd probably define it a little tighter as different geometrical arrangements. So different geometrical arrangements.
Like diamonds and graphene and graphite.
Yes. So that's another excellent example. So we have phosphorus and then, so carbon, yeah, you mentioned diamond, graphite, graphene. I'll put C60, which is a buckyball. We'll look at this in a second. All right, so let's look at that. And so I like Wikipedia for chemistry, so that's what I always tell people. I was like, usually the chemical information is pretty decent. I wouldn't try to look at history of recent events with Wikipedia. Anyways, so carbon, as you mentioned, that's known for its many allotropes. And I like this because we can appreciate the different structure. So A here is diamond. So what gives diamond its strength is the repeating tetrahedral structure. So at every point, this is a carbon. So it's just, again, repeating structure. So that's why diamond is so strong. And then if we go over to B, so this is our graphite. And you can tell that this is graphite since it's made in these 2D sheets, right? So now that's kind of showing you how the different structure leads to different function, right? So that's why you can write with graphite. So it's shearing off in those sheets here. And so let's see, I don't remember all of these. So obviously there's more on here. I'll point out, so the one that I was mentioning, C60, is D here. So this was a pretty big discovery. So this was at Rice University with Richard Smalley, where they were coming up with this buckyball shape. So they were making it. And then, of course, this became the foundation for carbon nanotubes, which is shown down here. So once they made this buckyball, then eventually they were able to synthesize these like nanorods, and now there's a whole vein of research about nanotubes and so forth. So Rice, like I mentioned, does a lot of that research since they discovered it. And then other ones shown here. So of course, you can also just have, right, an amorphous structure. So there's no really defined structure for carbon.
Would that be something like charcoal?
Probably, I'd have to double check that, but yeah, I think like charcoal would be more amorphous.
And then why is it that only carbon has so many allotropes and not anything that's in the same family as it?
I mean, so that leads to a lot of things. So carbon will cover it. So carbon is actually a lot smaller than you would expect, like with its radius. Carbon can also do like single, double, triple bonds, not only with other elements, but with itself. And so silicon, I would have to check where the research stands with it, but last I checked, they can't make like a ring of silicon like they can with carbon. So, and then that gets into why we're carbon-based life forms and not silicon-based life forms. So carbon is beautiful. And so then we mentioned phosphorus. So we'll look at phosphorus. So that has a few other known allotropes. And so, of course, white phosphorus is still used in warfare to this day, even though I think it's officially banned, but, you know, nobody follows that. And so, yeah, that's white phosphorus. And so that's pretty toxic. And, I mean, if you're bored, you can go look at the horrible pictures, but phosphorus will, like, destroy your jaw, and then you get, like, phossy jaw. And, yeah. And then red phosphorus. And so again, just another structure, trying to look at their structures here. And then violet phosphorus. So again, just different rearrangements of phosphorus. And so you can see that the violet phosphorus gets more inert. And then black phosphorus, so again, just different geometrical arrangements. And so again, some of these are extreme conditions. So that's the other thing about chemistry that I like to point out, right? So I think people sometimes get frustrated with chemistry because there's always like an exception or this and that. And it's also because like chemists are always trying to like push the bounds too, like, right, if something doesn't exist, well, a chemist is going to go try and make it exist or force it to exist, you know. And again, right, we have extreme conditions, so that's the beautiful thing about research is you can create all these crazy conditions and, you know, observe these very esoteric species. And so the last allotrope we'll look at to point out that's kind of common is sulfur. So most people don't know this, but sulfur is actually a ring compound. So it's this 8-membered ring. And I think we'll look at sulfur in lab. If not, I'll pull out some sulfur samples at some point. And then sulfur itself should not smell. It's just the degradation products that eventually lead to your sulfur being smelly. All right. So I'll add that on there as S8. Sulfur. All right. Probably want to think about doing our demo. All right, so I want to explode stuff for y'all. Kind of the problem, so if you were with me on Tuesday, you understand that we have to perform a hazard assessment. And so that's what I do as a chemist, mentally perform my hazard assessment. And I just don't feel comfortable, like we kind of have a little bit of space, but I don't want anyone in the front row to like accidentally get singed or scared. And so to be honest, that's why I really like to be in 132, and so I can do a nice big exploding demo. But we're in here. So I think what we're going to do is we're going to make a field trip outside. And so I'm thinking like in the courtyard downstairs would be a good place to try to do this, like outside, you know, on the first floor. You know what I'm talking about, the little courtyard. So we can go there as a class. I may need 1 or 2 brave volunteers who want to help me transport the balloons. And so, yeah, the only caveat with that, and so again, right, you need to perform a hazard assessment in your mind. And so why I'm trying to be very cautious is, right, I mentioned we're doing hydrogen, oxygen, and then the combo of that. Well, what's the issue with those gases? So yeah, they're pretty combustible, they're flammable, right? So I don't want to risk any like static shock incidents. So right, thinking of, now I always forget what it's called. These are the Hindenburg, the big blimp that blew up. Yeah, the Hindenburg disaster. So that was probably set off by like a spark. Do y'all know what I'm talking about?
Yeah.
Okay, I was going to pull it up. Oh, like, that's the beauty of the internet. Yeah, well, I can't spell. But, yeah, basically that's probably what led it to blow up, right? So back, they were using hydrogen to do these blimps, and somewhere there was a spark, and obviously the whole thing went up. So we don't want that to happen. Obviously, we're using small balloons, so, again, kind of thinking of how much thermal energy we could do if things go wrong. But yeah, we're not going to take the elevator with balloons, was my safety point with that. So again, right, you have to perform your hazard assessment. Well, you don't want to be in a trap room with a balloon that could be explosive. Same thing with like, you got to be very careful with gases. Like even liquid nitrogen, we will play with that at some point in this class, but you would not want to ride an elevator with liquid nitrogen, because what if the elevator got stuck? And then you have to think about all that liquid nitrogen being converted to gas, and then that could potentially, right, displace all the wonderful oxygen in the elevator. So things like that. So that's how I think as a chemist. And again, I'm trying to get y'all to start thinking like that as hazard assessments. All right, so let's try to make our field trip. Oh, but before people start moving, so we need to take our quiz, right? So we're still going to practice our quiz. It's just a welcome quiz, but after the demo, I just want to make sure that everybody comes back to take the quiz, because that's also how I'm going to take attendance today. So I'll just say, don't forget the quiz. And then, like I promised, we'll also go back and work on conversion factors. All right. Questions before we start moving around? I'm going to stop this stream, unfortunately. So usually I like to tape everything. So if you're gone, I usually tape a demo, but like I said, this is one demo that I don't feel comfortable doing in here.